For 50 years, physicists agreed on one thing about black holes. Anything that falls in gets compressed to a single point of infinite density, and nothing, not light, not information, not structure of any kind, ever comes back out. That was the consensus. Settled science. Then a handful of researchers started asking a different question. What if the crushing doesn't end things? What if it starts them? To understand why that question matters, you need to go back to 1915. Einstein publishes his general theory of relativity. The equations are elegant. They describe gravity not as a force but as curvature, mass bending the fabric of space-time around it. The math works beautifully for planets and stars. But the equations also produce a problem nobody wanted to talk about. Under certain conditions, the curvature becomes infinite. The math breaks. That breaking point has a name, a singularity. It is the place where general relativity admits it no longer knows what is happening. Einstein himself hated the idea. He suspected singularities were a sign that the theory was incomplete, not a real feature of the universe, but a gap in human understanding. For decades, most physicists agreed with him. They treated singularities the way you treat a warning light on a dashboard. Note it, move on. Then Roger Penrose changed the conversation. In 1965, he proved mathematically that singularities are not optional. They are inevitable. Any mass that collapses beyond a certain threshold must, under general relativity, produce a singularity. No exceptions. Stephen Hawking took Penrose's proof and extended it backward in time. The same math that predicted singularities inside black holes also predicted one at the origin of the universe. The Big Bang was itself a singularity. Here is where the logic takes a strange turn. If the Big Bang was a singularity, a point of infinite density that exploded into a full universe, then what are black holes? They are also points of infinite density. The conditions at the center of a black hole and the conditions at the start of our universe look, mathematically, almost identical. One produced everything. What does the other produce? That question sat quietly in the literature for years. Then physicists started taking it seriously. The physicist Lee Smolin put forward a formal version in 1992. His idea was called cosmological natural selection. The argument goes like this. When a black hole forms, the singularity at its core does not simply end. It bounces. The collapse reverses at quantum scales before infinite density is actually reached, and a new region of space-time inflates outward, not into our universe, through it, into a separate space-time entirely. A new universe on the other side of a black hole. Smolin went further. He proposed that child universes inherit slightly altered physical constants from their parent. The speed of light, the strength of gravity, the mass of an electron, all slightly different from ours. And universes that produce more black holes produce more offspring. Over vast timescales, the multiverse would evolve, by natural selection, toward universes finely tuned to make black holes. Our universe makes billions of them, which, Smolin pointed out, is exactly what you would expect if we are a successful descendant in a long lineage. But there is a hard problem buried in all of this. General relativity and quantum mechanics do not agree with each other. General relativity describes space-time as smooth and continuous. Quantum mechanics describes reality at small scales as granular and probabilistic. At the center of a black hole, both theories apply simultaneously, and they give contradictory answers. This is the singularity problem in its rawest form. We do not have a theory that can tell us what actually happens there. The equations fail, physically, not just mathematically. Stephen Hawking spent the last decades of his career on a version of this problem. In 1974, he showed that black holes are not perfectly black. They slowly radiate energy, what we now call Hawking radiation. Over immense timescales, a black hole radiates away all its mass. It evaporates. That discovery opened a new crisis. If the black hole evaporates completely, what happened to everything that fell in? The information, the quantum states of every particle, seems to vanish, and quantum mechanics says that is impossible. This became known as the black hole information paradox. Hawking initially believed information was simply gone, lost forever. Most physicists were horrified. Losing information would break the foundations of quantum theory, which has never made a wrong prediction in a century of testing. The debate lasted 30 years. In 2004, Hawking publicly conceded he was wrong. He accepted that information must somehow escape, encoded in the Hawking radiation itself, scrambled almost beyond recognition, but present. The question of how it escapes remains open. Loop quantum gravity offers one answer, and it also supports the bouncing universe idea. In this framework, space-time itself is made of discrete quantum chunks, roughly 100 billion times smaller than a proton. When matter collapses into a black hole, it cannot compress beyond the size of one of these chunks. The collapse halts. Then it rebounds. Carlo Rovelli and colleagues calculated in 2014 that this bounce could seed an expanding space-time region on the other side. The math is consistent. There are no infinities. The singularity disappears. There is also the firewall paradox, proposed by Ahmed Almhiri and colleagues in 2012. Their calculation suggested that at the event horizon, the boundary of a black hole, in falling matter encounters a wall of high-energy radiation, not a gentle crossing, an immediate and violent disruption of structure. If correct, the firewall makes the interior of a black hole unreachable in any conventional sense, which would also conveniently make the whole question of what happens at the center somewhat moot. Physicists have not resolved this either. Two hard contradictions sit in the same space. What makes the frozen universe idea genuinely strange is what it implies about our own origin. If black holes produce new universes, and our universe contains hundreds of billions of galaxies, each holding hundreds of billions of stars, many of which end as black holes, then our universe may have produced an enormous number of descendants. And we exist because a previous universe produced a black hole. Inside that black hole, the conditions were right. Space inflated. Physical constants landed in ranges that allowed stars, then carbon, then us. We cannot test this directly. No signal from the other side of a black hole's event horizon reaches us. No experiment we can run will confirm whether a child universe formed in the core of a collapsing star last Tuesday. That frustrates a lot of physicists. A hypothesis you cannot test is not, by the standard definition, science. Smolin himself acknowledged this and spent years trying to find indirect predictions, features our universe should have if cosmological natural selection is true. Some of those predictions have held up. Others have been challenged. The question is still alive. The image of a black hole as a dead end, a one-way drain that grinds matter into nothing, may simply be wrong. Every tool we have says something happens past the event horizon. We just cannot agree on what. General relativity says singularity. Quantum mechanics says the information survives somehow. Loop quantum gravity says there is a bounce. The universe you are sitting in right now may be the answer to that question, played out once, in full, inside something else's black hole. What do you make of that? Leave your take in the comments below.